Welcome to the next installment of Statistics in Pajamas. This time we'll be talking about the one sample z-test. We spent some time in past lectures talking about z-scores and how we could use that to identify how likely it would be to see a given observation value, right? But really, there's a lot more to using z-scores than just figuring out probabilities of a given observation. Often, you'll want to know something more about the larger population and how that compares to your sample. So remember, a sample is a collection of observations, a data set that you've collected, and if you've collected it properly, it should be representative of the larger population. So we can test for that to see if it is representative of the larger population. We can also compare our sample to other populations to see maybe if it fits those population distributions better. So the test that we use for that is the one sample z-test. But how did we know that? We talked about how there are several questions you have to work through when identifying what the correct statistical test is, and that this often depends on what your research question is. Well, the research question associated with the one sample z-test is that you want to know the probability of your given sample mean, whatever the mean is for those observations you've collected. You want to know the probability of that occurring compared to a larger population. There's only one group that we're testing, it's that sample, and we have an assumption that our data is normally distributed. So we have continuous data, it's normally distributed, and we're comparing one sample mean to the larger population. So if we go back to the steps for an inferential analysis, we'll walk through these one at a time. We know we have to start with a statement of the null hypothesis. Well, for that one sample z-test, we know that we're comparing the sample mean to the population mean, and the null hypothesis would be that they're equal to each other. There is no difference. So if we were to write that out statistically, we'd have an h sub naught where the sample mean, which is x bar, is equal to mu, the population mean. And the second step was to figure out what test we should be using in order to answer that null hypothesis. And so since we're looking for the difference between a sample mean and a population mean, we know that pushes us to the one sample z-test. To keep us honest, we want to make sure we set our standard p-value threshold, that alpha level, and let's just use 0.05. Now we have to analyze the data distribution. This is important because one of the assumptions of that one sample z-test is that our data is normally distributed. So we have to stop and make sure that our data is normally distributed before we proceed with the actual calculation of the test statistic. And it really doesn't look much different from our z-score calculation. Remember, the z-score was taking our observation value, which we're replacing with the sample mean, and we compared that to the mean, the overall mean of the sample. But in this case, we're comparing the sample mean. We're looking to see how different it is from the larger population mean. Now with the z-score, the straight z-score, we just divided it by the standard deviation. Instead, what we have now is the population standard deviation. So it's not an estimate of the standard deviation for our sample, but of the larger population. And any inferential test that you run is going to have to include some criteria that represents sample size. And here we're dividing that standard deviation by the square root of the number of observations that we have in our sample. This essentially adjusts this one sample z-test for the power of the test, right? For how many observations we have within our sample, and hence how close we're actually approximating the population with the sample we've collected. But what's interesting about this one sample z-test is it does assume that you know something about the population, right? You have to enter the population mean and the population standard deviation. But typically what we'll use when we're conducting a one sample z-test are means and standard deviations that come from very large data sets that are widely accepted, or from scientific literature. Perhaps there have been many studies published that look at a given metric across a population, and you can aggregate all of those studies and come up with a typical mean and standard deviation. Or sometimes it may just come down to professional experience, right? You could always say that expert A indicates that a typical mean would be this, and a typical amount of variability would be this. So those are all acceptable ways to figure out your population mean and standard deviation. The next step was to figure out what that critical value was that we needed to compare to our obtained test statistic. And so to figure that out, we just go right back to the normal distribution probability table that we used for our z-scores. Right? We know we have a p-value threshold of 0.05, and we know what these tables are giving us, right? They're giving us the probability of being less than a certain z-score. So if, for example, we were using a one-tailed test and all that 5% could be squished down to one side, we could just look in the body of the table for 0.950, right? And that, wherever that falls, here's 0.9495 and here is 0.9505. Our z-score associated with that probability is 1.64, and it's somewhere in between 6.4 and 6.5, so maybe we could call it 0.645. So 1.645 would be the critical z-value that we need to beat when we're calculating that test statistic in order to conclude that we have a significant difference between our sample mean and our population mean. If we're doing a two-tailed test, we know that that 5% can be split between both tails, which means really we only have 2.5% in this tail and 2.5% in that tail. So we'd have to be finding the value within the body of this table associated with 97.5% probability, and that brings us down to a z-score of 1.96. So if we were doing a two-tailed test, we'd actually have to be beating 1.96 instead of 1.645. So you can see that whatever we calculate has to be much more extreme if we are doing a two-tailed test as opposed to a one-tailed test. Keep in mind, if these tables are confusing to you, you can always come back and do this in Excel. Remember, we can use the norm S inverse function and plug in the probability that you're looking for, and it will return really the same value that you get in the table. So once you have that obtained value you've calculated, and you have the critical value that you've identified based on your significance threshold, you can compare the two. And if what you've calculated is less than that critical value, then you have to accept the null, and you have no significant difference. But if what you've calculated is more extreme than that critical value, now you know you can reject the null and you do have a significant difference. At that point, all that'll be left is for you to draw your conclusions and summarize those. And so I just wanted to give you an example of what that might look like. The one sample z-test does have some shorthand that you can use. Within these parentheses, you would say z. What this does is it tells us what test you ran, and you would actually list whatever the obtained value was that you calculated, comma, and then you would also enter the p-value associated with that obtained value. And how would you summarize all of that very succinctly in one paragraph? Well, I've given an example here. Remember, the key components of a summary paragraph would be to state what the hypothesis is, and I've done that here. We tested to see if there was a significant difference in body mass between our Vermont sample of long-eared bats and the larger population across its geographic range. The second piece is to report your actual results with the shorthand from the z-test. So I say, we found that Vermont bats were significantly larger than the population. I enter my z that tells them the test, my obtained value, and the p-value associated with that. Then comes the interpretation part. This is likely due to the cooler temperatures at the northern edge of long-eared bats' range and the thermal advantage of larger body size. So that's just a quick run through of the steps, but I think it's helpful if we actually go through an example. So imagine that we've gone out to 20 different pure eastern hemlock stands, and what we want to do is see if these hemlock stands are much more valuable in terms of carbon storage than typical forests across the Northeast. So we want to compare this sample of 20 eastern hemlock forests that we've gone out and measured above ground biomass and compare that to the larger population of a typical northeastern forest with mixed components. The null hypothesis would just be that there is no difference between total above ground biomass of our pure eastern hemlock when we compare it to average biomass levels for all northeastern forests. We're going to keep ourselves honest, set the level of risk, that's 0.05, so we're only going to say we have a significant difference if our resulting p-value is less than 0.05. We have analyzed the data distribution, and we know that we have normally distributed data. So again, choosing the right test. If we know that we're comparing differences between a sample mean and a population mean, we know we're using the one sample z-test. So then the next step would be to actually calculate that obtained value, that test statistic. And so we do have to know something about the larger population, and luckily we do. We know that for our hemlock stands, we have mean above ground biomass of 156,900 megatons per hectare, or megagrams per hectare. That would be a lot of carbon. And we know that our population mean from the literature is 147,101 megagrams per hectare. We know that the standard deviation for that population was 52,707, and the sample size was 10. So actually, sorry, I misspoke. We only had 10 hemlock stands that we were comparing for this example. And when you plug these into the equation, we come up with an obtained value of 0.5879. Okay, so this is what we calculate to quantify the difference between that sample and that population based on the power associated with this specific test. Right? So now we have to find the critical value. And again, it depends, were we doing a one-tailed or a two-tailed test? Well, we could have asked either way because we didn't specify that when we went into the null hypothesis. So it might have been a good idea for us to specify whether or not we really thought hemlock were going to have higher above ground biomass, or whether we were just looking for a difference in general. So let's assume that we know hemlock are long-lived, large, slow-decaying species. So we're actually hypothesizing that hemlock would be larger than the northeastern forests in general. And so if that's a one-tailed test, and I know I'm using that 0.05, I can find the 95% in here, and I can see that I have to beat that 1.645. Go back to what I actually calculated though, and I calculated 0.5879. So that means that while the sample that we collected does have higher above ground biomass than the population, that's not a significantly different difference in the means. It's not significantly higher than the population. What if instead of only having 10 hemlock stands that we'd assessed, we'd actually gone out and we had collected above ground biomass data for 100 stands? So now everything else is the same. Look at what this does to the obtained value. Right? We now have 1.859 as our obtained value. That really makes a huge difference, and it just shows you how sample size can impact the power of your test. So now if we were to compare that back to our table, 1.859, if we were doing the one-tailed test where we had to beat at the significance threshold of 0.05, where we had to beat the z-score of 1.645, right in here where we get to 95%, we've definitely beaten that. So if we were doing a one-tailed test, our 1.84 is more extreme than the 1.64 critical value associated with that one-tailed test. So we would say, yes, hemlock do store significantly more carbon than typical northeastern forests. Let me summarize that on one slide so maybe it's easier for you to wrap your head around. If we had conducted a one-tailed test because we hypothesized that eastern hemlock would be higher, and we had 100 observations, so we're still using that larger power sample, then we would have calculated 1.859, which is greater than the critical value for that one-tailed test of 1.645. Therefore, we have to reject the null and say that eastern hemlock is significantly higher than the larger population. But if we'd done a two-tailed test, even with our 100 observations, our obtained value is still 1.859, but because we're now doing a two-tailed test, that critical value has changed to 1.96, and 1.859 is not greater. It's less than 1.96, so we would be forced to accept the null and say that there is no significant difference. So hopefully this just gives you an example of, one, how sample size can influence your results, and two, how a one-tailed or a two-tailed test can influence your conclusions. Right? They both really have to be stated up front so that you know what you're doing with your analysis and you can keep your results clear and honest. So at this point, all that's left is summarizing your results. So again, I've just given you an example of how this might be written up, and the key pieces that I have to make sure are in here are, one, what was the original hypothesis I was testing. In this example, I've gone with the one-tailed test, and people will know that because I say that the eastern hemlock stands store significantly more. I'm also demonstrating the power of my test, and then I've listed how many stands I've used. I've included the shorthand here from my results, and I've interpreted why we may have seen these results. Notice I didn't just say p less than 0.05, but because we do have Excel or software like JUMP, we can report the actual p-value. So I simply went into Excel and I entered the norm s dist function with my z-score, which returned my probability. It actually returned the probability of being less than that z-score. So remember, to find the probability of being more extreme than that or greater than that, which is what my p-value is quantifying, I just had to take 1 minus that value. So hopefully now you have an idea of when you might use a one-sample z-test and how you would do that, walking through each of those steps. So until next time, enjoy your first foray into inferential statistics.